Okay, great. So yeah, I'm Ryan. I'm going to talk about location-aware path selection in Tor today, which is joint work with my friends and colleagues Florentin, Rochet, and Olivier Pereira at UC Louvain. Aaron Johnson, our great PETS chair at the Naval Research Lab, and Prateek Mittal at Princeton. So let's start with Tor, which is kind of the central part of this talk. And it is this system which proxies network traffic across a number of relays all around the world before the traffic reaches its destination. And Tor must be a system that network operators hate, because instead of taking the obvious path from the client down to the server along the coast of California, Tor decided to route traffic through France and then Chile and then Vietnam before eventually hitting its destination. And this leads to something like a 20x increase in geographic distance that the traffic had to travel. If you think I'm kind of cherry picking a scenario here, I fired up Tor browser, I connected to my server, which is not too far away from me, and the path my traffic took in Tor browser was from my location in Washington to Amsterdam, back to the US, then to Sweden, and then back to the US, so crossing the Atlantic Ocean 4 times. So it seems like we can do something about this. Tor is in some sense, a research system, so there are things we can change. And in path selection, I guess the two things that are obvious that you can change are the number of hops in a circuit and the way that relays are selected for those hops. Now, there are good reasons that we have 3 hops in each Tor circuit. Really, it's the smallest number of relays where no relay in the circuit can see both the guard and exit or entry and exit relays. But there is a lot that can be done in terms of the way that relays are selected for positions in the circuit. And indeed, Tor has looked at and implemented different path selection algorithms over the years. So maybe the most prominent change that Tor made in its path selection algorithm is the use of guards, which were introduced in 2006. And the general consensus there was if we pin an entry relay in that position for a long amount of time, we will limit exposure to adversaries. But there has been some uncertainty about what the right number of guards to use is. We've moved from 3 guards to 1 guard, and maybe 2 guards is the right number of pinned relays to use. Also, the way that Tor has incorporated bandwidth measurements into relay selection probabilities has changed over time, and even things like the use of IPv6 in the way that clients can connect to Tor relays changes the criteria by which Tor relays are able to, or by which clients choose Tor relays. Okay, so going back to this picture though, there is maybe a more obvious thing we could do in this scenario, which is why don't we prefer paths that are close to us? So in this picture, we have the client, and the client could prefer this short path, which makes a lot of sense because if we have 3 or at least some number of honest relays in the circuit, we still get the cryptographic protections that Tor provides, but now we've saved a lot of time connecting to our destination. And similarly, another client in a different region could also prefer its short path. And so this could really be a game changer in providing low latency circuits for Tor. In general, we call this idea location-aware path selection because it's a scheme where clients change their circuit construction preferences or relay selection preferences based on where they're coming from. So location here is kind of a general notion. It could mean either the location in the world, or it also could mean their location in a network. And there have been a lot of works exploring location-aware relay selection, probably over a decade of research, and we can do some really cool things with it. Like the idea I was exploring just a moment ago is really a simplified version of a system called LastTor, which does this exact thing. It prefers short geographic paths. There's also been works that try to mitigate network layer attacks. The Counter-Raptor system was designed to prevent BGP hijacks by choosing essentially relays that are close to you in the internet. There's also been systems where you could avoid popular ISPs that are likely to snoop on your traffic, and even systems designed to route your traffic around countries that you're worried about being adversarial. So there are a lot of these systems presented that have been designed over the years, but things go wrong when you consider these systems. There are still problems with these systems, and there are reasons not to use them today. So what can go wrong here? So I'm going to start with or basically go through these examples with LastTor, although I'm not trying to pick on LastTor explicitly, or only like these problems apply to most location-aware path selection algorithms. So we'll start with something called a TimeBased Attack, or a time-based attack, which was presented 2 years ago at PETS. And here's the idea. Let's say I'm running a web server, and I notice an unusual message come to my web server. It's some anonymous thing, and it looks like it's some weird love letter. And if you think that this is crazy, I don't care. It's my story. I can do what I want. But if you want to make it more realistic, maybe you could say it's about Bitcoin or something, and then it becomes a lot more topical. Anyways, I noticed that day after day, I receive these messages from Tor exit relays. Someone anonymously is dropping these messages off at my server. And I'm really curious. I want to know who is sending these letters to me. So I am diligent, and I save my Apache logs, and I write down the IP addresses of the exit relays that are sending me these messages, and then I do some geo-IP work, and I find out that all of these relays are located in Algeria. And what that means is, because LastTor prefers relays that are close to the client, I almost have a area of suspicion. I can now target, or I have a strong candidacy for where that client is coming from. And if I do a Google search, I find that this person, Alice from Algeria, wrote a paper that fits the bill, so I can immediately suspect that Alice is this person who is sending me these messages, and I've effectively defeated the cryptographic anonymity properties that Tor provides. But this is almost like a probabilistic de-anonymization. I'm not certain that Alice is really the one who's dropping these messages off. So what else can I do? I can, whereas the TimeBased attacks are relatively passive that I described, the relay placement attacks that I'm going to describe now involve me becoming more active. So if I suspect Alice, one thing I can do is introduce some relays into her geographic region. Maybe I can run some VPSs and just introduce some more relays. And because of the local preferences that LastTor uses, it's likely the case that Alice will end up choosing some of my relays. And when that happens, I have a lot more power as an adversary. I can start launching traffic analysis attacks, or if I get all 3 hops in the circuit, I can really effectively de-anonymize the traffic that goes to the network and link Alice's connections, which is really bad. And it's worth noting here that this is an attack that Tor deals with in general. At any time, I can run some relays and try to attack clients, but the location-aware path selection makes it disproportionately cheap to attack Alice, because I don't have to run a lot of resources before it becomes really likely that I'm able to get on her circuit. And then the third issue that affects these location-aware systems is load imbalance, which I really couldn't fit into the story that I was telling, but the idea is simple. If the distribution of users in the network does not match the distribution of relays in the network, it means that we'll have some load imbalance here. The clients on the Northeast region will prefer their relays, which really don't have the capacity to serve the number of clients in that region. And if the load were distributed differently, we might be able to actually service these clients. It's just the imbalance that the location-aware algorithm cause that's creating issues. So at this point, you might be thinking two things. The first thing you might be thinking is that these problems are somewhat manufactured. And to that, I'll say that these are all demonstrated issues with these systems. There are empirical analyses that show that these are real things, and the attacks can be performed by real adversaries at low costs. And the second thing you might think is that all of these problems are pretty obvious. And I hope that you do think that, because they really aren't too hard to understand. But it's worth noting that it's taken over a decade of designing these systems and presenting them for us to even get here, and we still don't have a system that is resilient to all of these flaws. So that brings me to our framework for thinking about these problems, which we call CLAPS. It just stands for Client Location Aware Path Selection. And the realization is that it's kind of tricky to do all of these things at once. So we have some goal like minimizing path distance, but we don't want to throw off load balance, and we want to prefer relays in certain locations, but we don't want to prefer them too much because that leads to this relay placement attack. And we don't want to leak location information over time. And another goal you might want to have is that we don't want to make things worse for some people than Tor is today. So for example, we don't want to make paths shorter in France but longer in the US, because that could damage those users, and those users who are in the damaged region might really need the protections that Tor provides. So there's a lot to balance here. But if you squint at this problem a little bit, it kind of begins to look like a constrained optimization problem, which is exciting because formulating it in a constrained optimization framework means that we are only going to consider solutions that path selection algorithms that satisfy certain hard criteria. So for example, we can enforce that relays have balanced load in expectation, and we can enforce that relays are not selected with too much probability. And then if we formulate this, for example, as an LP, and we found that we could formulate some of these path selection algorithms as a linear program, then we can just let the optimizer choose the best path selection algorithm from within this constrained space. So this is really exciting. I hope you don't feel cheated by me not showing you all the variables and formulations, which I think are largely mechanical. I think the real magic is in the formulation or viewing the problem this way. And if you squint at this again, you might realize that I left out one constraint, and that is we don't really want to leak location information either. And that's trickier to capture in the framework of an LP, it turns out, or we didn't think of a great way to do that. So we introduced the second idea, which is the idea of a location guard. And really, I think what it boils down to is that you just coarsen the number of potential locations that the clients could come from. And so you choose some representative locations around the world, and you just have all clients always pretend like they're coming from one of those few locations, so that even if you leak information, you can only learn up to the location guard, and each location guard still has a large anonymity set associated with it. So combining these two ideas, we were able to build better path selection algorithms. We tried plugging in a different objective function to this LP framework, and we built a better Counter-Raptor, one which actually achieved higher BGP resilience than the original Counter-Raptor design, which is surprising because we placed explicit constraints on the solutions that we could obtain, and still we were able to actually achieve a better objective value than what the original designers were able to achieve. And I think the insights there as to why that might be possible, one is that whereas the original authors use heuristics to achieve certain goals, we're able to actually specify the problem as a explicit optimization problem. And so we're not using heuristics to try to prevent placement attacks or maximize resilience. And another thing that is important to realize when dealing with location-aware path selection is that relays can be used differently depending on where you're coming from. So a lot of time it's thought of that Tor guards are guards everywhere, and Tor middles are middles everywhere, because that's kind of how the network is today. But it's totally possible that we could weight positions differently by location. So for example, clients in the United States might choose a relay as a guard, but clients in France might choose that same relay as a middle with higher preference. And that was able, I think, to also give us some more flexibility in the way that we're assigning probabilities and achieving resilience. Okay, so that's really it. During discussion, I really would like to hear from the Tor folks about whether this idea is right for Tor. And despite all of these systems being designed, I don't think any of them have really been seriously considered. So really, I want to get a better understanding of what the barriers are to Tor and if this is a good idea. If that the benefits that these schemes provide kind of outweigh the implementation complexity, and also if transparency is an issue. So it might be difficult for Tor to adopt a location-aware scheme if it makes it harder to understand how the Tor network is working. Also, there might be some interest in using linear programs or optimization frameworks to formulate Tor's path selection today. And then, yeah, if there's these things are hard to get right. So if there's other tools we could use or design to help researchers get these problems right, I'd love to have that discussion. So thanks for your time, and that's what I've got.